Okay, so it got disconnected. Okay, so let us start for the second question. And this second question, it states that we are having one second. So we were discussing this question. It states that a possibly non-uniform stick of mass m and length L lies smoothly frictionless ice. Its midpoint, which also serves as a center of mass, is in contact with a thin vertical pole fixed on the ice. One end of the stick is given a quick blow perpendicular to its length, causing the center of mass to move away from the pole. Determine the minimum possible value of the stick's moment of inertia about its center of mass such that stick does not strike the pole. And for that we have drawn a stick, and in this I have drawn a uniform stick, but ideally it is non-uniform, and this non-uniformity is not mentioned how it is non-uniform, so that doesn't matter at all. And L is the length, and at the center of mass, suppose this is the center of mass, and we have a pole, okay, and this is just connected in contact with this particular pole, and an impulse or it is given a blow perpendicular to its length. So somewhere here we are applying a force, okay, and we have to find out the moment of inertia about the center of mass such that the stick does not strike the pole. Okay, it should going to miss the pole. So this is our pole P, and this is also our center of mass of the stick. They should be not, it should not hit the pole. And for the sake of convenience, let us assume that this stick is lying on our xy plane. So this is our x-axis and this is our y-axis, and the center of mass is having a coordinate of our origin, that is 0, 0. And so for our left side we can say this will be minus L by 2, and on the right side we can say that will be plus L by 2, and impulse, that is our J, is being applied at our plus L by 2, okay, and that is in the positive y direction. And for our, we can say that if our velocity of center of mass is our Vg, so we can write that our immediately after the impulse, we can write that our velocity of our linear velocity of center of mass immediately after the impulse, linear velocity of our center of mass, and let us suppose that is our Vg, and that will be in y unit direction, and we can say that this velocity will be equal to the impulse and its mass, which is given to us as m. And we can also find out the angular velocity, okay, with which it is going to rotate, and that we are going to find out once again with respect to our center of mass. Therefore, we can say that our angular velocity, which is suppose omega about our center of mass, and that is our omega is equal to this is our impulse j, and lever arm is our L by 2, and moment of inertia is suppose our I, where I is the moment of inertia about its center of mass. I is equal to moment of inertia about center of mass. And for the sake of convenience, because we can write that, let us define a ratio. So we define a ratio k, and that ratio will be equal to our this velocity of our center of mass and divided by omega, and this ratio is will be coming as our v of g is our j upon m, and omega is our j L by 2 upon I. So this comes as our j, and j are going to cancel out here, and this will be coming as our 2I upon m times L. So we are interested in this ratio because none of the other parameters are going to matter. Okay, so it means this ratio is nothing but it provides a relationship between our linear motion speed, that is our Vg, to our angular speed. Okay, that's the only purpose of this ratio. And we can, for the sake of convenience, we are going to find out the motion equation of the points on the stick. Motion equations of points on the stick. And suppose all these points are is denoted by a variable, and that variable let's define as our s. So we can say, consider any point on the stick at a distance s from the center of mass. From our center of mass, therefore we can write that our s is going to belong to our minus L by 2 to plus L by 2. Okay, within these limits, the point s is going to behave or lie. And we know that our stick is going to rotate as well as translate. Therefore, we can find out its position at any time t. Okay. So we know the stick rotates and translates. So position at time t you can say so position at time t of this point, here this point is nothing but point S, and this point S we can take anywhere on our stick. So it is going to have two coordinates, x coordinate as well as our y coordinate. So we can say that our x coordinate will be nothing but our horizontal axis, and this horizontal axis, that is defined our x with respect to distance s as well as time t, and we can write this equation as our x will be equal to s comma t. Initially it was at position 0 plus, and it comes as s cos of theta, and theta will be equal to our omega t. And similarly we can write for our this y coordinate, or we can also say that the point moves in a circle around the center of mass as the stick rotates. Okay. Therefore our this x position coordinate is going to oscillate with our s cos of theta. Okay, so we can just write it as, because this is simple 0, so this comes as s cos of omega t. Now we come to our y coordinate. And y coordinate is our vertical axis, and which we can denote as y s comma t, and the vertical coordinate, it will be moving as y of our s comma t will be equal to our vg time t plus s sine of omega t. Okay. So our center of mass moves linearly with the speed v of g, and additionally it will move vertically due to the rotation, which is our sine of omega t. Therefore we can write that our center of mass moves up linearly at speed v of g, and the point additionally move or rotate additionally moves vertically due to rotation, and the rotation part is our sine of omega t. So which basically means that the initial position of our stick was our somewhere like this, and we were having a pivot point, or we can say the pole which was at the center of mass, and we applied the impulse at one of its extreme end. Okay? And we have taken that our this center of mass is our origin, so this is our x coordinate and our y coordinate. So we have to find out that this entire stick should not touch this pole after the impulse is being applied, and for that we have to suppose to find out its moment of inertia. So which basically means that it will try to rotate somewhere like this, and this extreme end should not touch this our pole. And so we can presume that suppose at any time t the stick position is something like this. And so based on this we have two types of, you can say, coordinate of our this point S. So we have taken the point S anywhere, okay, on this stick. And so one second. Okay. So let us suppose it moves by the angle of theta. So obviously this angle will be also equal to our theta. And we have taken, let us suppose S is a distance of the point from our center of mass. So now we can find out the coordinate of this position with respect to our vertical motion as well as our horizontal motion. In case of our vertical motion, we have to keep in mind that our center of mass is moving with the additional velocity of our v of g. Therefore, the distance covered by in time t will be equal to our this v of g multiplied by t. So this is our distance along with the rotational part, which is our s sine of omega t, and with respect to this s we can find out the total distance from our vertical part. And so we know that our pole is fixed at origin. Okay, so we have already decided that this is our origin point. Okay. So let us come back to our original question, that was our when the impulse is being applied. Okay. So we can say that our strike condition, and therefore we can write that, okay, and we said that pole is at our origin. Okay, so let me write it here. So we said that the pole is fixed, the pole P is fixed, and that fixed is our 0, 0. So it means if any of this stick is going to touch this pole, that particular you can say that particular point will be having the coordinate for fraction of second will be equal to 0. So which basically means that suppose this is our pole P and we have this coordinate as 0 and 0, and let us suppose this stick for a fraction of second is going to touch this point P. So now if this point is our S, so at that particular moment the S is going to have our coordinate as 0, 0. Okay, so this is a basic presumption or conclusion we can draw from here. So it means if the stick touches the point, this point P, at any given time, that particular point is going to have a coordinate for a fraction of second that should be equal to 0, and which we don't want. The stick should not touch the pole. Okay, so this is the basic, you can say, conclusion which we can draw from this particular discussion. And the pole P is fixed at 0, 0. Therefore we can say the stick will strike the pole if at any time t greater than 0 there exists a point S on the stick such that the x coordinate of that stick the coordinate of that point should be equal to 0 and y coordinate of that point should be also equal to 0. So if this condition is satisfied, the stick is going to touch our pole. Okay, that's a basic. And we are going to test this condition, whether we are going to put first x is equal to 0, then later on we are going to put our y is equal to 0. So let us examine these conditions. So we can say that from x is equal to 0, and we already have our x coordinate equation, that is our s cos of omega t. Therefore we can say that our s cos of omega t is equal to 0. So either we can say from here that value of s is equal to 0, and or we can say that our cos of omega t is equal to 0. Okay, so these are the two conditions which can be true. And if s is equal to 0, we have said that this s is the distance of that point from the center of mass. So if s is equal to 0, so we can say this is nothing but our center of mass. And we come to our second point, that is from y is equal to 0, and we already know the equation for our y, that is our v of gt. So which means that v of g times t plus s sine of omega t is equal to 0. From here we can calculate our value of s. So we can say our s will be equal to minus of v of g times t divided by sine omega t. And so let us make an analysis of our when x is equal to 0, or we can say for our s is equal to 0. So we can say that analysis of x is equal to 0. So which basically means that for s is equal to 0, we can write that our y, which is our vg of t, because if you put our s is equal to 0 in this equation, this entire term will be coming equal to 0. So our y will be equal to only vg of t. Therefore we can say that y is equal to vg of t, and which will be equal to 0 at t is equal to 0. Okay. So it means there is some kind of initial contact, okay, after the, and it is not after the motion has started. Therefore from here we can write that which is initial contact and as it's not after the motion starts. Therefore, we can just ignore this part, because at the start we are given in the question that the stick is just touching our pole. Okay, stick is in contact with the pole. This is given in question, and at the start means at t is equal to 0. So from here we just proved, or we can just came conclusion that our t is at t is equal to 0, the stick is in contact with the pole. Okay, so this is nothing but our initial contact, but we are supposed to find out after the rotation. And we come to our secondary part, that is our cos of omega t is equal to 0. Therefore, from here we can say that omega t is nothing but our theta, which is equal to our pi by 2 plus n pi, and this is for n greater than or equal to 0. So it means at these rotation angles, we can write that our sine of theta will be equal to minus 1 raised to power n. Therefore, our s will be equal to minus of minus 1 raised to power n, and this comes as a Vg times t. Okay. And we know that our point S should be lying between minus of L by 2 plus L by 2. Okay. This is the basic condition, that point S will be lying between these two boundaries. Okay. And therefore, you can say that for collision, you can say that the point S should be less than or equal to our L by 2. Okay. And let us find out the first critical time of potential strike. Potential strike means potential collision. So we can say that our first critical time of potential strike, and we can write that our theta, which is our omega t, will be equal to our pi by 2, smallest positive t basically. Okay. You can say smallest positive t. And for this value of theta, we can write that our sine of theta, which is our sine of pi by 2, is equal to 1. And from here we can say that our S is equal to minus V of G times T. And T we can write in terms of our pi upon 2 omega. And we just wrote that our S should be less than or equal to L by 2 for collision. Okay. Therefore, we can write that for collision at this time, is our V of G pi upon 2 omega should be less than or equal to L by 2. And now we come to the ratio K, which we have already derived. Therefore, we can say that ratio K is our V of G upon omega. So we can combine this V of G and omega. We get this as our K, and we have our pi by 2 is less than equal to L by 2, which gives us that value of K should be less than equal to L upon pi. And we also know that our K is equal to 2I upon ml, which I have already derived. Therefore, we can say this 2I upon ml should be less than equal to L upon pi. And from here, we can say that our moment of inertia is less than equal to, we can write this as our ml square upon 2 pi. So this is our value of our moment of inertia, so that the rod or stick does not strike the pole again after the impulse. And we have to find out the minimum value. Therefore, we can say that our moment of inertia of minimum about its center of mass will be equal to our ml square and divided by 2 pi. If this is the value of the moment of inertia, the stick which was lying this horizontally, and there was a pole somewhere along its center of mass, and when the impulse is applied to the other end, the stick is not going to strike this pole again. Okay, it is going to freely move away from this particular pole. Okay, so that is our moment of inertia, which we are supposed to find out a minimum value of moment of inertia about the center of mass. And this point P is, we have assumed is, or point P or this pole is also our origin, and this we also have assumed our center of mass. So total length was given to us our L. So our left side will be minus L by 2 and the right side will be our plus L by 2. So these were the two questions for today. So this completes the two questions. Thank you.